everyone to this our science demonstration lesson. In this particular lesson, we're looking at the use of the STEM integration approach and the application of the engineering design process. With me here today, we have some budding scientists. On my right, we have
Stephen
and
Stefan.
And on my left, we have
Tamoya, Lysandra,
Grayson. So as you can see, boys versus girls. Here we go. All right, so for this particular session, we're guided by these questions. What is STEM integration? How can we utilize this in lesson planning? And how do we make use of the engineering design process? All right, so of course, with the MSc, STEM is presented as more than just STEM subjects. It is really a problem-solving approach that is to be used across subject areas. And here, we're utilizing some learner-centered approaches such as inquiry-based, problem-based, and project-based learning. And these are used to solve authentic problems. Okay, so the goal here for STEM integration is really to help students develop skills. But before we look at that, let us find out what this acronym really means. What does STEM mean and what does it represent? So, Grayson, what is the S? What does the S represent?
Science.
Science, all right. Stephen, the T?
Technology.
Technology. What about the E?
Engineering.
Engineering. And the M?
Mathematics.
Mathematics. All right, so really the STEM approach is an interdisciplinary approach, right, that is used where we apply scientific and mathematical concepts and we deliver it through the use of tools. They can be high-tech, low-tech tools, technology tools, and we use them to develop solutions to real situations, right? And of course, when we include the arts, then we refer to that as STEAM. So we're really going to be using this approach in this particular demonstration. So the E, we want to pay a little more attention to the E, because the E is not just engineering. For the NSC, the E is the problem-solving approach. So whatever approach we use to solve the problems, that is the E, right? And we have two methods that we normally use, right? We can use one,
Scientific method.
the scientific method, and two,
The engineering design process.
all right. So anybody wants to tell me a little about the engineering design process? What do you think that is?
I can go ahead.
Okay.
The engineering design process is basically a problem-solving method that engineers use.
All right. Okay. And what about you? Anything to add?
This process would really help persons solve problems by creating products,
Yes.
right?
Yes, and even to improve on products.
Yes.
Great. All right. So let's look a little at some of these two methods. So these are the steps in the engineering design process. Let's go. So number one step, Grayson, ask. And here we're asking questions. We're defining our problem so we know what it is that we're trying to solve. All right. Two, Lysandra. Imagine what happens in that step, Lysandra.
Brainstorm ideas and choose best idea.
Best ideas. Beautiful. So that is about researching, right? And the third step is
Planning.
what happens in that step?
So you're basically planning forward and gathering information that you need.
Great. And number four, Stephen, what's that step?
Create.
What are we creating?
Over.
We're creating our
Work.
product or our model, depending on what it is that we're doing. Or even a process, because even in computing, your process that you go through to write your algorithms, right? That can be used also with the engineering design process. All right, and of course the fifth stage is
Improve.
what happened in that step, Stefan?
We've already tested our design, and now we're just improving the flaws and weaknesses.
All right, I hope you don't improve the flaws, but yeah, we want to improve it to make it better. Great, all right, good job, guys. All right, so let's look at the second method is the scientific method, and as shown, again, you have a series of steps. You really have some similarity between the scientific method and the engineering design process, of course. But for the scientists, you're really going to be conducting an investigation, right? So you, again, have your observations, ask a question, then you make a...
Hypothesis.
Okay, what's the hypothesis?
It's really a guess.
A guess, right? But the guess is based on, things that you would have observed, right? Great, great. So it's not just any old guess, it's an educated guess, right? And then we do that, what after that?
We conduct an experiment.
Conduct an experiment, and from the experiment we get our,
Conclusion.
before we get our conclusion, we get our
Results.
results. And you use your results to get conclusion. Beautiful. All right. And then, of course, as scientists, you report those results. All right. So let's go. So STEM integration, we're saying, is a method. It's learner-centered, right? As pointed out before, it is using different areas, right, to solve real problems. So the aim is to develop problem-solving skills and to construct new knowledge. And the focus, of course, is on looking at solutions for real-world situations. Again, let's look at the fact that you want to present open-ended problems. So let's see what else we can find out about STEM integration. Open-ended problems. So it's not a problem where there's a yes or no answer. You're looking at problems that are rich for students to get a certain content from. They can produce many different solutions, all right? And of course, they are real world, so they require an integrated approach. So let's get into this particular method. So we're presenting here a scenario, all right? So we've shown some images, right? I'm going to ask our scientists what they're seeing in the picture. What are you seeing in the picture, Stephen?
Flooding.
Flooding, all right. What about you, Stefan? Flooding, okay. What do you think would have caused this? What are some of the possible things?
A storm.
A storm,
Drain blockage.
drain blockage,
Climate change.
climate change. Why do you say climate change? What is it that climate change does?
So climate change, first stage is basically a long-term change in the weather. So it could have caused, as Grace Ann said, it could have been caused by a storm that climate change would have.
Would have initiated, right? So because of climate change, we know there are many different effects. We have, apart from extreme flooding and changes in weather patterns, we have also other effects such as, anybody?
Change in temperature.
Change in temperatures, right? Great. Anything else? Anything else?
The changing the way people live.
The way people live, yes?
Because the heat would affect people from going to their workplaces because they're scared they might faint.
Okay, all right. What about organisms? Does climate change affect them?
Yes. It could
In what way?
cause their habitats to be damaged.
Great, right. So we know of the famous thing about the melting of the polar ice caps, right? Which is going to affect organisms that live in that region of the world, right? Great. Okay, so of course that's a real issue. But apart from that, let's see how else it could affect us immediately here, right? So what are we seeing in this picture now?
Landslide.
Landslides, all right? What do you think could have caused this landslide, Stephen?
Like soil erosion.
Soil erosion, right? Great. Anybody else?
Could have been caused by flooding.
Flooding as well. So the same impacts of climate change could have resulted in these breakaways. Now when we have these breakaways, I mean, we would have had examples in Jamaica of breakaways. What are some of the things that happen as a result of this? When we have breakaways, what happens?
People can't get to the places they want to.
Mm-hmm. Anything else?
And the food can't be transported.
Food can't be
Might
transported.
locked inside of the community.
Right, yes. Anything else?
Many accidents can occur.
You can have accidents. All right. So essentially, there are a lot of things that could happen. We're zeroing in on the fact that if communities are shut off, when you have, for instance, breakaways, people cannot access in or out, cannot go in or come out of their communities, right? And so there are other problems that can occur. So we're going to present these students with a scenario. Here is a scenario. So let's look at the scenario, students. You're living in a section of the island that has just experienced days of flooding. Okay, so you're putting yourself in that situation. It has resulted in road breakaways that would have prevented residents from accessing life-saving supplies like medicines and food and so on, right? So they're cut off and we need to find a way to reach them. All right, so here is what we're suggesting. We're thinking, let's go, that we want you to design a catapult device. Anybody knows what a catapult is?
Yes.
Okay, all right, I hope. All right, which we're going to use. So you're going to design it. So you're going to go through that engineering design process. All right? Looking at your problem, looking at the possible solutions, choose one, make your model, and so on. And you want that device to transport the life-saving medication to this community that has been marooned. You're using only these materials provided. Let's see what we have here. What are these, Stefan?
These are popsicles.
Popsicles, another name for it, Stephen?
Six.
Fudge sticks. What else we have here?
Paste.
Blue.
Glue, yes, paste or glue, yes, paste as well. We have here
String.
I would say string or what?
string, and this is,
Straws.
which are outlawed now, yes. Tacks. What are these, Lysandra? Corks. More pops, fudge sticks, yes. We have here spoons. What are we going to use spoons to do? Then we have
Tape. Rubber band.
rubber bands, and of course you have your trusty scissors. Be careful, no cutting unless it's necessary. All right, so the students are going to now be left to work through how they would construct their device. So you can go ahead, talk with yourselves, communicate, collaborate, and figure out what you're going to use to design your catapult. Here's an example shown here. That's just an example, of course. They can go on their devices and look up possible designs. Go ahead, students, all right? And there must be a criteria, of course, to determine the success of this device. And so we're going to show you what we're going to use to determine this, the success of this device. So to determine if their device is actually meets the expectations, they're going to be using this flow chart, which has been put into different sections based on color. So the midsection would represent the community. That's where they want the food or the medication or whatever it is that is needed by the community to land. So when they make their device, they'll come here and they will test that device and try to land the material in the middle. That's the red section, and there are certain points for that section, which is about 40 points. Then they will go to the orange section, and you can see the criteria on your screen. They would be getting 40 points if it lands in the red section. If it lands in the orange section, they'll be getting 30 points. In the green section, of course, that means that they're far from the community, right? Community won't get any food or medicine. They would get 20 points, and of course, if it's outside of that, then the community would starve. Oh dear. Anyway, there's also points allotted for the materials that they use, how well they use everyday materials, their originality, their creativity. So there are also points. There are also points given for the use of materials, as can be seen, about 20 points. How original they are, how creative they are in their designs, that's another 20 points. Their use of time, did I tell you how much time you have? No, I didn't. Anyway, and of course they have to work together, collaborate to make this. You really should be making one device, you know, unless you're making it and you're going to test out all of them, but you're working together to create one device. Collaboration. So decide which design you want and decide on it. All right, so the students are busy making their catapult devices, which they're going to test in a little while. So while you're working it out, and you can go ahead and test it, because you're just testing to see if you need to do your improvements. All right? They can, of course, improve on their device. So what these two questions we want you to be considering as you make your device: what will make it more accurate? What adjustments you would make to make sure that it works? Right? Ladies?
Yes.
Two questions on the screen for you to bear in mind. All right? So you can go and test out before we actually have the actual demonstration. as students work through this particular design, you see that they will be going through the stages of the engineering design process. All right, and so they want to basically work through those stages, and as was indicated, if necessary, then they would have to go through that loop all over again. As you can see, this particular task and this particular approach requires time for the students to be able to work through the problem, come up with their designs, do their testing, make their improvements before they present their actual designs. And of course, we want them to be working together. So students, we wanted to indicate the steps that you would have taken, the problem, as you understood the problem to be, what was the problem, what did you do after that, right? Outline the steps that you would have taken to solve the problem, and of course we're going to discuss and test your particular solution, and then we're going to peer assess to see which one worked. We will have presented the rubric already based on the different zones, the color of the zones, and so as each group tests their model, we will add the points to know which one would have been the best at solving the problem of giving the community some life-saving supplies. Now to test our devices. So before we look at the actual demonstration of the testing of the model, we want to ensure that we will identify the problem correctly and come up with our steps or solutions to the problem. All right, so can somebody remind me again, what was the problem? What was the problem, Stefan?
That the road was a road of town or area was broken away and needed to transfer food and different objects to it.
Food and things like medication and so on, right? Or whatever the community needed, right? So the problem was we wanted to transport some supplies to this community who would have been cut off because of whether it was some major landslide, some flooding, or something of that effect, all right? So we're going to ask Timoya's group to tell us the steps that they use to treat with their problem, and then of course we'll come back to Stephen's group.
Alright, so first we stacked 5 fudge sticks on top of each other.
Stick a pin. Before you went actually to make your device, did you do anything else before? You researched, all right? And in your research, you found out what?
Yes, we found steps. helping me a Santa Claus.
Okay.
Visual of what it would look like.
Okay, and you made a choice. Okay, obviously. All right. So after you made that choice, you chose a particular design. So what was that design?
So it was. Should I just show them exactly?
You can show and then explain what
So
you did.
this is what the sand made, and basically you stack 5 more sticks on top of each other, and then you put rubber bands on each end, and then you get 2 more fudge sticks, and then put rubber bands on only one end. I chose to use 2 because you'd have more support, and then you would put the 5 stacked fudge sticks into the 2 stacked fudge sticks, so they would create something looking like this. And then you'd put more rubber bands in the middle where they would meet, so it would be secured, as Lysandra said. And you can then tape or glue or whatever you like to do to secure a cork or a spoon on the end of one foot that would be in the air, and launch.
Okay, launch. And launch they did. They were testing out their devices earlier. What about you, gentlemen? What were the steps that you used to come up with your design? Can you explain what you did here?
So first,
You can hold it up so that they can see.
so this is our finished product.
Mhm.
So first we stack 10 fudge sticks together and use rubber bands at each end to wrap it together. Then we'll place 2 pairs of fudge sticks in between
Mhm.
the stacked fudge sticks.
Oh, so you didn't put it on the outside, you put one in between.
Yes.
Any particular reason?
Not really.
Not
Just
really?
originality.
Originality, okay, sorry.
And at the tip of each fudge stick, 2 corks and are held together with 2 thumbtacks.
All right, and you would have also tested your device? Okay, and have you made, when you were testing, did you make any adjustments, ladies?
Yes, we did.
Like, adjustment for what?
So, we're thinking that if we push this up more, like make this go all closer to the edge as we could get it, that this will be more wider and it would like have more space
To go further, or so you wanted it to go further? All right.
We also decided to put like a spoon instead of a cork because the cork was a bit difficult to.
You stick it outside. All right, good. So you did some adjustments. Any adjustments you made, Stephen?
After testing, we added 2 more rubber bands on each fudge stick to give it a little more resistance.
Oh, resistance. So here we go, talking about resistance. All right. And when you were actually making your tests, any adjustments you made while doing the test? Actual test. Did you do any adjustment?
Yes, the distance from the starting point
Yes.
and the angle I was
And
fired from.
So you looked at varied angles and so on. Anything to add?
Any other adjustment would be the spoon.
Yeah, okay.
So I added 2 corks.
Or you had used a spoon before and then you changed. All right, great. So we are going to now test these designs. So they have 3 chances to land this supply to the community, to land it in the red zone, of course, as mentioned before. If it lands in the orange zone, then they will get a certain number of points, and if they land in the green zone, then they'll get another set of points. There's also marks for collaboration, the use of materials, and of course, creativity. So, let's go. Team 1, ready?
Ready.
All right, let's go. We're gonna test your design. You have 3 chances.
Should we just use all of
You decide. I don't know what you're doing. You're supposed to be working together. All right? So, turn around. Yes? Make your decision what you're doing. You have 3 chances. And I might add a 4th depending on how close you are, but 3 chances to get into the red zone. Here we go. fine. All right, they're doing one each. All right. Okay, one more chance. Remember, you need to be right behind that line, yes? All right, so your persons will have to swim and other things to get that food. All right, let's see the guys. Leave it there. I might give you a fourth chance, don't worry. All right, young men, let's try your design. Let's take up this. One sec. You have coins? Okay, good. Three chances. All right, don't worry.
Good.
All right. Since nobody got close, I might give you all another chance. Another 3 sets. All right, green again. All right, you get another 3 more chances. And then that's it. So both persons landed in green. Let's see if we can get it closer to the community. Orange or red? Go ahead, ladies. Go again. All right, gentlemen, come on. A bit. Go straight to the side. All right, let's go again. 3 more chances. We want somebody to get close. Close, Grayson, not far, close. Woo! Yippee you! All right. All right, let's see who else wants to try. All right, you're in orange. All right, gentlemen, 3 more chances. Behind, or just right there. All right, take your time. All right, bingo. All right, so our community is saved. Oh, don't see any joy in any faces. We saved the community. We brought them food and medicine. All right. Go ahead, shake hands, shake hands. All right, so both groups got their devices to land in the red zone. Our community is saved, of course, based on the devices, the solutions given. We can get students to make some critique. And suggest if they needed to make any improvements. So here, I mean, a very simple activity, but it would have made use of the engineering design process that we want our students to use. So we want to look at this particular different aspects of the STEM approach. So we had already mentioned that STEP, this S stands for science. So I want you to see if you can identify, students, any particular science concept that we would have targeted in this activity.
Teamwork.
All right, before we reach teamwork, science concept, like an area of science, so a particular, you were saying something before, you use the word resistance, yes? Experimented, but in terms of the concept, you would have been looking at, for instance, your use of, your catapult device represented a what? A machine? Do you think it was a machine?
Yeah.
Did it represent a machine?
To some extent.
What type of simple machine did it represent? Okay, you don't remember nothing about simple machines. whatever simple machine it would have represented. Alright, its answer is coming, yes?
It would have represented the lever.
Yes, the use of a lever. You remember levers? Long ago, but yes, levers, yes. And there are other science concepts that would have come out, right? Of course, the technology would have used these different materials. Low tech, of course, but it can be used, right? They would have also done research with their devices, right? That's also using technology. They would have made use of that engineering process, okay, by going through the steps that we indicated earlier. They added their little flair in terms of their creativity, right? How they would have used their materials, and any mathematical concepts you thought wasn't included? Angle, because you had to change the angle to project it, right? What about you? Any mathematical concept that would have come out?
The power that you put in order to release.
Release, all right, that sounds more science, but well, science and maths are all, of course, related. Yes? You agree. All right. So, of course, we can use this scenario, this activity, come a little closer, yes, to carry out different things, and just to make sure that we understand, these are really the concepts that we would have targeted. So throughout the discussion, we're talking about effects of climate change, what landslides result in, erosion, right? Remember? Mm-hmm. So those are science concepts, yes. We would have, for mathematics, looked at our measurements, although we probably didn't actually use a ruler. We would have done some estimations, right, in terms of how we would have, released our projectile, right? We looked at angles, as Grayson said, and we tried to get it in the correct section. And of course, we use our engineering process to come up with a solution. And for science, again, we would have mentioned the different machines, because this is really a simple machine. All right, good. And we would have ensured that we adjusted our force, remember that? Mm-hmm. And the motion of the device. So there we have it. We would have made use of the STEM integration approach, right? To get these young scientists to solve a problem that is really a real world issue. Certainly we have seen it in Jamaica, where communities need access to certain materials. So, as we end this particular demonstration, how confident are you, teachers, in using this STEM approach in planning your lessons? Let us hear from you. Find a way to email us and tell us, and so that we can know. Thanks for joining us.